In last lecture, we have shown that for large-scale TSP, we have the TSP distance is around a constant times the square root of a times n, where a is the area, n is the number of customers or destinations. So now we'll first give you some clues about how can we find the TSP tool which support this estimation. So that is, can we provide a feasible solution? So we still take the square as the shape for the surface area. So if we have a square area and then our entire surface area size is A, and then they are evenly distributed n customers. So how can we create a feasible TSP tour? So let's consider a interesting heuristic. We will decompose the entire area into small sub-areas, and then we call each of these sub-areas a swath. And then definitely there are some dots evenly distributed in each of these swaths. And then if we start from one point, and then we may travel across some of the swaths, and then we can go to the nearby swaths, and then travel back, and then keep doing this. We need to find a way that can go back to our origin. So in this case, we can try to consider our decomposition contains a swath that with an opposite direction, and then we will go back. So that means we can decompose the entire area with some equal distance swaths, and then with this width, we can try to decompose the area into multiple swaths, either vertical or horizontal, such that we can finish a TSP tour. An interesting observation is that there are multiple ways we can decompose our area into this swath. For example, let's consider a small surface area, and then we can decompose it into, so our path can be this way, this way, this way, this way, this way. The path can go this way, this way. So this tells us the decomposition of this swath is not unique. But an interesting result is that the entire TSP tour can be decomposed into two types of movements. One is called the longitudinal movement. The longitudinal direction means we travel along the direction parallel to the longer side of this swath. And also we have another movement, we call it transversal movement. So that means we travel along the direction parallel to the shorter side of the swath. And then we can observe that the longitudinal distance is related to the length of the swath, and then the transversal distance is related to the width of the swath. So then let's consider the L1 norm distance. So for the L1 distance, let's consider a swath. We have some points which evenly distributed in a swath, and then our travel should be going through a transversal distance, and then going through a longitudinal distance, and then going through another transversal distance, and then going through a longitudinal distance, and so on. So in this L1 distance example, we can see that the total TSP tour distance can be considered to be the total longitudinal distance, or the length of the swath. This is a longitudinal, plus the traveled transversal distance between each visit on the customer dots. So if we sum up all the swaths together, we can rearrange the shape of the swath if needed. And then the total summation of all the longitudinal distance will be the summation of the length of all swaths, which is the area, divided by the width. And the total transversal distance will be the number of customers times each of the distance times the average distance for each visit. Let's see the exact distance between each visit. Okay, so the longitudinal distance is relatively easy to calculate. And then let's try to estimate the average distance for the transversal travel. So the transversal travel, in fact, can be considered as we have a line with distance W, and then because our customers are evenly distributed within this swath, so that means we will randomly pick up 2 points. And then what is the expected distance between these 2 points? Okay, or let's take a simpler example. We can just consider a unit line segment 0 to 1, and then if we pick up 2 points, which is x and y, they all satisfy a uniform distribution. So then our question is, what is the expected distance of the larger point of xy minus the smaller point of xy? So this is our question. So how can we calculate this? Let's consider the joint distribution of xy. Let's see, this is x, this is y, and this is distance d, or let's use d. So the distribution of x is from 0 to 1. The distribution from y is 0 to 1. So we know that when x equals to y, and then the distance between x and y is 0, and then when x is 1 but y is 0, and then the distance between x and y is 1. Similarly, when y is 1 but x is 0, the distance between x and y is also 1. So to this end, we can draw a surface. So this surface gives us the distance between x and y, given all possible combinations of x and y. This is symmetric, and then each part of this surface is a triangle. So let's take this triangle, and then so at this corner point, the distance is 1, and then at the bottom edge, the distance is 0. So the average distance for this triangle actually geometric center, so which is 1/3 times the height. Okay, so that indicates average distance between x and y is 1/3. You can also use calculus to prove this. Here we just skip the proof. So with this, we can tell that for a general swath with width SW, the average distance between x and y will be W/3. Okay, so in this case, we can calculate the total TSP tour by the summation of its longitudinal distance and then it is transversal distance. So we have, and then this can tell us how we choose the width of the swath. Right? So this is the EOQ structure. So that can tell us the minimum distance for this TSP is equals to, and then this is when this width equals to square root of 3a divided by n. So since this is a feasible solution, so it can tell us in L1 this optimum TSP constant for L1, which is smaller than this feasible TSP tour. Now let's extend the shape from square to rectangle. And then definitely for square, we are relatively easy to determine how to align the swath. But for the rectangle, this may be a little bit tricky. So let's assume here the length of the rectangle is L, the width of this rectangle is L prime. So recall that if we can successfully decompose the area into swaths, let's say if we can have the swath which is very narrow, and then we can definitely easy to find a feasible TSP tour. Remember, if we can decompose it into this swath, the distance is equals to longitudinal distance plus transversal distance. And here the area becomes L times L prime. And then to achieve the optimum solution, we know that this is equal to, and then when we can have our width of the swath. Okay, but the situation may be more complicated in rectangle is because the width can be dramatically smaller than the length. That means when the rectangle is very narrow. So in this case, we may not be able to decompose a very narrow rectangle into multiple swaths. Probably the best we can do for a very narrow rectangle is just we decompose it into two swaths and then go from one direction and then go back. So in this scenario, that indicates that our EOQ formula cannot achieve this optimum solution in its first order when its gradient equals to 0, satisfies first order condition. So in this case, our width of the swath is somewhat bounded. So in the special case for this narrow rectangle, we can see the condition that we cannot easily decompose the area into small swaths is when our actual width of the swath is smaller. So this tells us the ratio of the short edge of the rectangle over the long edge of the rectangle is smaller than 12 divided by number of customers n. Under this case, the length of the swath is 2L. The longitudinal travel of this TSP is 2L. And then the transversal travel distance would be 1/3 times the width of the swath times the number of customers. Okay, so in this case, we can get our optimum solution. This is the first one is when L prime is smaller than 12 divided by n, and also divided by otherwise.